Many situations are modeled well by random variables that take on exactly two values. In these cases where we have a binary random variable, we can always use the Bernoulli distribution to classify what type of random variable we're dealing with. So if a random variable has a binary outcome, then it is said to follow the Bernoulli distribution. So what is the Bernoulli distribution? Well, suppose that x is a random variable and it takes on either a value of 0 or a value of 1. Importantly, these outcomes can be anything, right? They're frequently going to be referred to as a failure for x equaling 0 and a success for x equaling 1, but any two possible outcomes could be mapped to the value of 0 and the value of 1. This is just a language game at this point. If this is the case, then no matter what the probabilities are, it's referred to as a Bernoulli distribution. And the Bernoulli distribution is always characterized by a parameter p. The parameter p is going to represent the success probability. And so here, p is going to be the probability that x equals 1. Right? We call 1 a success. P is going to represent the probability that it equals 1. And so if you know the success probability, then you know everything you need to know to characterize this distribution. And specifically, the probability mass function is always going to be equal to p to the power of x times 1 minus p to the 1 minus x. Right? The values are either 0 or 1. And then we can use that to figure out that the expected value of x is always going to be p, and the variance is always going to be p times 1 minus p. Right? So if you have a binary outcome, x represents a binary outcome, you can map those values to be either 0 or 1, right? And then from there, we know the probability mass function, we know the expected value, and we know the variance. Okay, so looking at an example here, suppose that in a practice, the particular hockey player that we're thinking about has 35% chance of scoring in any shootout attempt. X is a random variable that takes on a value of 1 if they score, and a 0 otherwise. So this is Bernoulli because either they score, which is a success, or they don't score, which is a failure. Right? So it's two possible values, 1 or 0, and we know the probability of a success. So what's the distribution of x? Well, x follows a Bernoulli distribution, and here p is going to be the probability that they succeed, which is 0.35. What's the probability that x is equal to 1? Well, immediately, we can already just say this, right? We know there's a 35% chance that they score, but we could also turn to the probability mass function, right? So we need to plug 1 in there. We get 0.35 to the power of 1 times 1 minus 0.35 to the power of 1 minus 1, which is just 0.35, right? Because then we get 1 minus 0.35 to the power of 0, so that gives us a 1, and all of that cancels down. Okay. What is the expected value of x? Well, because we know it's Bernoulli, we know that the expected value of x is equal to p. And so here p is 0.35, and so the expected value of x is 0.35. What's our standard deviation? Standard deviation is the square root of the variance, right? The variance in this case is p times 1 minus p. So that's 0.35 times by 1 minus 0.35, right? Take the square root of all of that, and you get 0.47697. Right? And so by identifying that this is a Bernoulli random variable, we get all of this information for free. We don't actually need to calculate it. We just need to know the value of p, and then we plug that into our formula. Second example, suppose that we have a fair 6-sided die. We use the die to play a game where the object is for us to roll a 6. Define a random variable x and state its distribution that maps on to the game. Well, in the game, we can either win or we can lose. Right? Winning is a success, and so we could make that a value of 1. Losing is failure, so we could make that a value of 0. And so then x could take on a value of 1 if we happen to roll a 6, and it could take on a value of 0 otherwise. Right? In this case, we could then think about, well, what's the probability that we roll a 6? It's a fair die, and so the probability is going to be 1 out of 6. Right? And so this is going to be a Bernoulli random variable with a success probability of 1 over 6. Right? So let x have a value of 1 if the 6 is rolled and 0 otherwise. The probability that you roll a 6 is 1 out of 6, and so this is a Bernoulli 1/6 distribution. Now, what's the variance of x? Well, in this case, the variance is always going to be p times 1 minus p. Right? P is 1 over 6, so 1 over 6 times 1 minus 1 over 6. Right? That gives us 5 out of 36. And so identifying that it's a Bernoulli makes it quite straightforward for us to calculate the variance. Now suppose that we actually make this game competitive. If the first player rolls a 6, they win. Otherwise, the second player wins. So let y represent the corresponding random variable for player number 2. We want to compare the expected value and the variance of y to that of x. Okay, well, y is going to be a Bernoulli 5 out of 6 random variable, right? It equals 1 if player 2 wins, and it equals 0 otherwise. Probability that player 2 wins is 5 out of 6. And so what's the expected value of a Bernoulli 5 over 6 random variable? It's just equal to p. P in this case is 5 over 6. So the expected value of x is 1 out of 6. The expected value of y is 5 over 6. These simply represent the individual winning probabilities. X wins 1 over 6 of the time. Y wins 5 over 6 of the time. For the variances, the variance of y is going to be 5 over 6 times 1 minus 5 over 6, which actually gives us 5 out of 36. This is exactly the same as what we found for the variance of x. And so the expected value of y is higher, but the variances are the same for both x and y. Okay, so the variance is equal, even though the expected value of y is higher than the expected value of x. Okay. Now, there's a quick note that's worth making on the language when we're thinking about Bernoulli random variables. Anytime that there are binary outcomes, no matter what those binary outcomes happen to be, it's going to be a Bernoulli random variable. Okay. We always refer to x equaling 1 as a success and x equaling 0 as a failure. This is the common language that we'll use for the Bernoulli. However, sometimes this language is pretty unreasonable. So for some examples, we might have x being a Bernoulli random variable that tracks whether a particular plane crashes, which would be x equals 1, or not, which is x equals 0. Of course, it's a little bit ridiculous to call a plane crashing x equaling 1 and being a success, right? But that's where the success is sort of divorced from what we actually mean here, right? Similarly, we might have y being a Bernoulli random variable that tracks whether a patient tests positive, so that's x equals 1, or negative, x equals 0 for some random or for some rare disease, right? Again, testing positive for a rare disease is not a success. However, we tend to refer to this as a success anyways. The idea is that we can always map this onto a coin flip, right? So success becomes heads, failure becomes tails, right? These are just labels that we give, right? And so if it can be modeled in the same way as a coin flip, maybe not a fair coin, but a coin flip nonetheless, then it's a Bernoulli random variable. Okay, so the Bernoulli distribution occurs whenever we have a random variable that has two possible outcomes. The distribution is characterized by the probability of success. And once we know that the probability of success, then we know everything that we might want to know about this random variable. We know its distribution, we know the distributional summaries, and we're able to immediately calculate those values.